So this is an example of using the LFO object in the control voltage library. So here I am creating two different LFOs. The red trace is LFO1, the green trace is LFO2. Notice that the amplitude of LFO2 is much lower because I set the amplitude lower when I created the object. I set the wave shape, the frequency, and the amplitude of these directly there. I'm also setting the bit depth of the LFOs. Now the bit depth is related to the amplitude, so if you try to set the amplitude higher than the bit depth, you won't be able to, basically. So the bit depth is just kind of keeping everything in check. Okay, so the LFO is a little bit different than the other objects. It's a signal rate object, right? So we do need to, just like we do for the main control voltage object, we do need to have a loop in our main loop to generate new samples for our LFO. Now, we really don't need to do anything inside of our control loop because the LFO is just generating an LFO continuously. So LFO2, nothing is going on in the control loop. All we're doing is calling LFO2 here, and then in our signal loop, we're getting the value of LFO2 and then writing it to our DAC and writing it to our monitor right here so we can see it. And there is our sine wave modulating the frequency of this oscillator. So pretty straightforward. For our oscillator, for LFO1, I added a bunch of things inside our control loop to modify our LFO. So we can do a couple of things. First of all, we could change the frequency of our LFO just by calling LFO1.freq and then passing in a new frequency. Notice that I turned this off just by using an if0 statement. I have a couple of things turned on. One is just change the shape of our waveform. So all of the waveforms in the LFO can have their shape be modified. So here we're taking a look at a ramp waveform, and the shape of this ramp waveform is changing. The blue trace is the shape. So when it's in the middle, here it's the unmodified shape, and then when it's at the bottom, it's kind of kinking the waveform one way, and then when it comes towards the top, it's kinking the waveform the other way. So that's a ramp waveform. When it comes to be a square wave, it'll just affect the pulse width. So you see the width of the square wave will get narrower and wider. And then when we get to a sine wave and a triangle wave, it's going to skew the waveform in different ways. One other thing I'm doing here is, as we can see, in our plotter, we're actually changing the waveform. So this is the logic to go through and change the waveform periodically so we can see what different kind of waveforms are available. So here's our sine wave being skewed. You can see it's kind of like leaning towards the right now, and it's going to be leaning towards the left when the shape resets. In our signal loop, all we're doing here is we are getting our LFO values and writing them to our DAC and writing them to our monitor. I'm also monitoring our shape just so we can see it, but this shape is not getting sent out the DAC at all. It's just being monitored for our own sort of edification. So if we take a listen to it, here's our sine wave, and here is our triangle wave right now. Here's our ramp waveforms. Notice that you can hear a little bit of clicking and popping at the discontinuities. Right there, right? You can really hear that. And then the square wave too, because it's such an abrupt square wave. So probably what I should do is smooth out some of those abrupt transitions to get rid of some of those digital pops from those really abrupt transitions. One other fun thing about this is that these are LFOs. Theoretically, you can increase the frequency as much as you want to. There's really no limit. The sampling rate is only 1 kilohertz, so going above 500 kilohertz is going to be maybe a little bit unpredictable. But if I set up to 200, let's see what happens. So I'm going to take our sine wave and plug it in over here, and we can just listen directly to the sine wave that's coming out of the ESP32. Well, that sounds pretty ugly. A lot of sort of pitch variations and whatnot going on. And the reason for that is because the serial printing is really slow, right? So if I comment out all the serial print code and upload it, we should get a little bit more of a more consistent result. And that sounds a lot better, right? So it is totally possible to use this at audio rates. Obviously, this is a poor representation of a sine wave, but hey, I don't mind that. Let's see what happens if we go above 500 hertz. We're going to start aliasing, right? So I do something really crazy like that. We're just going to get either 200 or 300 hertz, right? So something sort of a little bit unpredictable. Anyways, yeah, lots of fun.